So today we're going to begin heat engines, refrigerators, and then the second law of thermodynamics, and that should end our chapter, our unit on thermodynamics. We will start with electricity and magnetism after that. Okay? So everything we're going to do today, we have seen, except for the second law of thermodynamics. It's going to be processes, isobaric, isochoric, isothermal, in a closed cycle. So just some words you will hear. A heat engine is any machine that converts heat into some work, and it uses a cyclical process. Okay. And let me see here. Yeah, so we can represent a heat engine as follows. So let me write here, heat engine. So it converts heat into useful work. So it takes heat called QH, QH here. That's the heat, the fuels it burns. And then if we give you some work out, we do work for you, but then always wastes some QC, some heat to the outside. A heat engine typically operates between two temperatures or more. The two temperatures we say, they're called heat reservoirs. So for example, a heat reservoir is basically something that's so large, its temperature cannot be changed. So if you go to let's say the Pacific Ocean, the temperature right now is something, let's say it's 10 degrees Celsius. If you jump in it, or I jump in it, it's 37 degrees. The temperature of the ocean is not going to change because of me. Not appreciable, not much. So we just say that's a big body of something, and it's a thermal reservoir. Okay. And it has just one temperature. So you can have a hot reservoir and a cold reservoir. So we like to also talk about when you have a heat engine, we want to talk about the efficiency of the heat engine. So first of all, by conservation of energy, you got energy coming in, energy, work being done, and then heat leaving this way. So the heat that leaves plus the work that's done must equal to the total heat that has entered. So by conservation of energy, we have QH must equal to QC plus W. QC plus W. Then there is the thermal efficiency. Eta is called the thermal efficiency. This is, it's supposed to be, so we don't want to write N because the number of moles is N. And so it's eta, and spelled this way. And it's the thermal efficiency. It's the thermal efficiency. Now, how would you define thermal efficiency? You would define it in an intuitive way. You would say what I get versus what I pay for in ratio to the ratio of what I get to what I pay for. So you get work done, and then you have to pay for the fuels that it has consumed, which is QH. Okay. So that's the thermal efficiency. Typically, the thermal efficiency is well, it has to be a number between 0 and 1. The efficiency cannot be more than 1. You cannot get more work than the heat that has entered. You can't put in 1 joule of heat and then get somehow 2 joules of work. So it has to be, W is less than this one, and it will always be less than 100% of 1. Now, another way you can write it is, by the way, W here is the work done by the system. The work done by the system. So W here can be eliminated. You can rewrite W as QH minus C. So you can say it's QH minus QC divided by QH, right? Because that's W. And if you simplify this, you have QH over QH is 1, and then QC over QH. So they're equivalent, but sometimes you have the QC and the QH, and you don't have the W, and you don't want to go and find it. So this is more convenient. But sometimes you just have W, and you just divide by QH, and you get your thermal efficiency. Okay? So, again, what you're going to see today is basically what we have seen, nothing new, up to the second law of thermodynamics. Okay? So, what we're going to do is examples of two heat engines, and then an example of a refrigerator, and then we'll try to do the Carnot cycle. It's a heat engine called Carnot engine. And there are many other cycles that can be. So let's get to it. You can get your calculator ready, and the rest. A big chunk of today's class is calculating, and it's stuff we already know. I guess it's a good review also. So here's the first example. The first example here. We have this clockwise cycle. So what kind of an engine is it a heat engine or a refrigerator? Heat engine is clockwise. And the cycle is, it goes from state 1 to state 2, isobaric, from state 2 to state 3, isochoric, and then from state 3 to state 1 is isothermal. The pressure at state 1 is 200 kilopascals, and the volume is 200 cubic centimeters. Not just it's cubic centimeters. So we need to, because at the end we're going to get W and the heat and so on. They're all in joules. So we need our volume to be in cubic meters and our pressure to be in pascals, not kilopascals.
It just lingers cube.
And then again, and then at state 2, the volume is 600 cubic centimeters, but the pressure is still 200. And then at state 3, the volume is 600 cubic centimeters, and the pressure is something that we need to determine. Pressure is something that we need. And so the question is, find the net work. There should be space here. The net work per cycle. Find this heat engine's thermal efficiency, and then find the power output. If it runs at 600 RPM, we will talk about that in a second. And then we're assuming it's a monatomic gas. Our gas here is monatomic. Okay? This gas is monatomic. So with all of these heat engines or refrigerators, it's advisable that you make two tables. One of them is with the states, and you need to list the temperature, the pressure, and the volume for each state. And then if you don't know something, determine it and make sure you fill out the first table. And then using the first table, you can do the second table. Okay? So let's fill out the first table here, just reading things, as many as we can from there. So first of all, the temperature at state 1 is 300 K, right? And the temperature at state 3 is what? 300 K, because it's an isotherm. They're connected by an isotherm. So it's 300 K for state 1. It's 300 K for state 3. Okay? 1 and 3, they're connected by an isotherm. Let's look at the pressures. The first, P1 is 200 kilopascals and P2 is 200 kilopascals. So I'm going to write it as, so 200 times 10 to the 3. That will be 2 times 10 to the 5th, right? Pascals. So it's 2 times 10 to the 5th pascals. And then state 2, the pressure stays the same, so it's 2 times 10 to the 5th pascals. Let's look at state 3 electronomal volume. It's just less than 100. How much less? We'll figure it out. Let's look at the volumes. It seems like we have all of them. We have 200 for state 1, but I have to multiply by 10 to the minus 6, right? So it would be what? 200 times 10 to the minus 6. So that would be, 2 times 10 to the minus 4. So I would write it as 20 times 10 to the minus 5th. Because I'm going to multiply these numbers later. The 10 to the 5th, 10 to the minus 5th, they cancel. So it's more convenient to write it. Okay. And then for state 2, it's 600, but times 10 to the minus 6, we'll write that as 60. That's 10 to the minus 5th, and then 60 times done with the table. We need just these two. Oh, sorry. Okay. So for this temperature here, you don't have to work that hard to do it. You don't need to. You actually don't need a calculator to find this temperature. Let's see why. In going from state 1 to state 2, did the pressure change? No. Did the volume change? Yes. What happened to it? It tripled. So PV equal to nRT. So PV, the left side, tripled because V tripled. So the right side, in order to maintain equality, it must triple. The right side must triple. So nRT, nR they stay the same. So the T that needs to triple. So you need to triple T. So what must this temperature be? 900. So you don't really need a calculator to do this one. So it's just right here. 900. Okay. The next one is the pressure. Let's go to for state state 3. Right? State 3. Look at state 3. What happened? From state 2 to state 3, what happened to the temperature? Decreased by what factor? It was 1/3, right? It's 1/3 of what it used to be. The volume is the same. So the right-hand side, the nRT part, the right-hand side is 1/3 of what it used to be. So the left side needs to be also 1/3. So the volume is the same, so that it's the pressure that must be cut to 1/3. The pressure must be 1/3, so it should be this number divided by 3. So it would be 2/3 times 10 to the 5th. So it's going to be this number, 2/3 times 10. So we don't need to do calculation, at least not yet. Okay. It seems like we would need the number of moles at some point because we need NCV, delta T, and so on. So why not calculate the number of moles right away? So we're going to do that. So how do I get the number of moles? Okay, two different things. With an N we get. Yeah, for one of the states, yeah. So PV equal to nRT, and just solve for N. So why not just use the first state that we come up to, and then use that. So we have this. N would be PV over RT, and so you can use P1 and V1, R, and then P1. P is this, 2 times 10 to the 5th, and then V is 20 times 10 to the minus 5th, 8.314 for R, and then the temperature is 300, and we get our number of moles. Notice that, remember that 10 to the 5th, 10 to the minus 5th? That's what it's going to be. I will just copy the number. It should be 0.016. Yeah, let me write this one before I forget. And now I can answer. For state 3. Yeah, so this is an isotherm. So whatever the temperature at 1 is, it would be the same as 3. Yeah, and since 1, you can see this one. So anywhere on this line, it's 3. So we got the number of moles, so that's good. Our next job is to find these things here. Some of them may be zeros, so let's fill in the zeros. State 1 to 2, is there anything 0? Is W 0? No. Q, delta E thermal? No. How about from 2 to 3? Yes, no. Yeah, W should be 0. From 2 to 3, it's isochoric. So the work done is 0. So that's something that we can write. So good. That's a 0. How about from 3 to 1? Is there anything that's 0? The thermal energy has not changed. Yeah. The only way to change thermal energy is to change the temperature. Isothermal. Good. So now it's time to actually do some work. So far we were escaping doing any calculations. Let's see. We need to do some calculations. Smaller chunk. So let's go from this one. I will write on the board here. It's going from 1 to 2. Again, W here refers to the work done by the system, right? From 1 to 2, it's isobaric. So the pressure, not the pressure, sorry, the work will be what? P times delta T, yes. Because it's the work done by, right? I'm not writing the word by the system. It's just understood. It's the work done by the system. Okay, so the pressure is 2 times 10 to the 5th. Times the change in volume. The volume went from this number to this number. So it would be 60 minus 20, and then the whole thing comes 10 to the minus 50. So 60 minus 20 times 10 to the minus 5th. So 10 to the minus 5, 10 to the 5. And 2 times 40 is 80, right? You have 80 joules of work. You get 80. I will always double check. What mistakes? Yeah, 80. Next, we need to find the Q. Q is, how do I calculate that? NCP, yeah. NCP times delta T because it's constant pressure. The number of moles is 0.016. CP is what? 5 halves. It's monatomic. Yeah, so 5 halves. R. 5 halves R. And R, of course, is 8.314. The change in temperature. Yeah, it went from 300 to 900. So I will write it all. 900 minus 300, so it's 600. Yeah. And we get our Q. So you have to multiply. We get copy. It should be 200. Delta E thermal?
8 minus 80 plus 200.
Yeah, we can use the first law to find the change in thermal energy, or we can use NCV delta T. Either way, right? Up to us. So we can say it's minus W, the work done by the system, plus Q. That's one way to do it. So let's just do it that way because it's easy. So minus 80 plus Q, which is 200. You get 120. I'm going to write these. Yes. Yes. And you probably should, just to double check. Yeah. I'll give you a minute if you want to. Yeah. It should give you the, it will give you exactly the same. And these tables are kind of like a puzzle sometimes. And if you can solve that puzzle without doing too many calculations. So for instance, for the change in thermal energy, we're done. We don't need to do any more calculations because what should the change in thermal energy be for the whole cycle? It should be 0. For the whole cycle, it should be 0 because we return to the same state. So, and when I add them all, right, for the whole cycle, I need to get 0. So what should I put here? Yeah. Yeah, take the 120. For Q and W, they would be equal to each other. Yeah. So, yeah, we would get to here. Oh, I'm sorry. You're here. You're talking about here. Oh, yeah. Yeah, you're right. I didn't even So for this one, see, once we found this, what should Q be?
Minus 1.
It should also be minus 120. So let's write it down. So from 2 to 3, we know W is 0 because it's isobaric. So Q is simply equal to delta E thermal, which we said is minus 120. So minus 120. So that saves you some calculation time, right? Instead of putting like NCV delta T and having to plug in. So that saves you a little bit. Okay, let's go to these. From 3 to 1, it's isothermal. It's isothermal, so delta E thermal is equal to 0, and at the same time it's minus W plus Q. So that means Q is equal to W. And what's W, the work done by the system for isothermal? NRT. Natural log of what? Yeah, the final minus the initial. In here, the initial is 3 and the final is 1. So it would be V1 minus, V1 over V3. Okay. So we got the number of moles is 0.006. R is 8.314. And the temperature, in going from 3 to 1, is 300 throughout. 300. Natural log of, what's V1 over V3? Yeah, it's 200 over 600, which is a third, right? Yeah, it's 1/3. So the volume, it has compressed. 1/3. So the work done by the system, we expect it to be negative, right? Because the system shrunk. So we expect the negative number. It will give us a natural log of 1/3. So multiply. I have about minus 44. So, what's the total work done? It's, yeah, you add these, that will be 36 joules of work in that. So let me write it here. W total is 36 joules, right? You add those. Let me show you for the heat that enters into the system and then the heat that leaves the system, right? So QH is the heat that enters the system. Let's see. So this one is positive 200. So we got 200 joules entered the system in going from 1 to 2. So we can represent it this way. Going from 1 to 2, 200 joules entered the system. So that's QH. That's the heat that entered. Going from 2 to 3, what happened? Heat was leaving the system, left the system, right? 120. So 120 joules left. I put just 120 and they left, it means it's negative. And then these 44 joules here, in going from 3 to 1, they also left the system. So you got 44 joules left. Left the system. So that means QH, the heat that entered the system, is 200. The heat that left the system is how much? 164, yeah. 164 left the system. And we leave it as positive, as plus. It's just understood that it left the system. So that's what QC is. The heat that was left. Let's answer we already answered A. What's the total work that per cycle? So in one cycle, how much work do you get total? 36. So that's the answer to A. For B, the thermal efficiency, eta, is the work, which is what? The total work in the cycle is 36, divided by the heat that enters, that was consumed, is 200. And so this is 0.18 or 18%. So that's 18%. Answer C. Any questions on this so far? We will see what's the maximum efficiency. It depends. It depends on the operating system. So now, they want to know if the engine's power output, or what is the engine, this should say, what is the engine, it's a question, or find the engine's power output. If it's operating at 600 RPM. What does 600 RPM mean? 600 revolutions per minute, cycles per minute, right? So we have this. So the engine is giving you 36 joules of work per cycle, right? Yes? That's the work it does for you every cycle. That's the work done every cycle. But then the engine is operating at 600 cycles every minute. So let me multiply that by the number of cycles per minute times 1 minute for every 60 seconds. And this will give me the power output per second, the joules every second. 600 over 60 is 10. 10 times 36 is 360. It's 360 joules every second, which is known as a watt, right? So 360 watts. Yes. One revolution, yeah, it's understood that revolution is a cycle. So it depends on the context. So a revolution in the context of something actually rotating, it's one circle in that case, right? So in this case, we know the engine completes one cycle, let's say it compresses, it goes back. So when it goes from 1 to 2 to 3 and back to 1, that's one cycle. So it's telling us that it's completing, it's doing 1, 2, 3, 1, 600 times every minute. So that's what it means. So that's the first one. The next one would be familiar. It's more of the same. It's a different cycle, but we will do exactly the same approach. So should we move on to the next one? All right. So we will move on to the next one. I need to lower this board here. Yeah.
So with Q total, you just add up all the Q values and it should be 36.
Yeah, it should be equal to the work. Yeah.
All right.
Yeah. Can I lower this one? Because I need to write on the board. And the next problem is here. So for this next one, for a change, we're going to use a diatomic gas. It's going to be diatomic. And that's the cycle. And you're given that the temperature, this is given. the temperature at step 4, at state 4, is 300 Kelvin. So the temperature is given at state 4. And so we're going to use this to fill out first table, and then we'll fill out the second table. So that's the order we go on. Right. Okay, so let's look at the, in this case we know all the pressures and volumes. It's just a record. So, state 1, what's the pressure? 3 atmospheres, right? And atmospheres are no good. We need them to be in terms of pascals, because we're going to get joules. Okay? So we need pascals, so you need to multiply by 1.013 times 10 to the 5th. That's what and 1 atmosphere is equal to pascals. So doing that, I'm going to just put here. So state 1, it's 3.039 times 10 to the 5th pascals. State 2, it's the same, no pressure change. States 3 and 4 are the same, and they're just 1 atmosphere, so 1.013 times 10 to the 5th. 1.013 times 10 to the 5th. And then the volumes. The volume at step 1 is 1, and the volume at step 4 is also 1. Steps 2 and 3, they have the same volume of 3 cubic meters. All right, so I'll give you a moment to now think about the temperature. Don't use your calculator. You can do it without a calculator, okay? You have to be able to just look at it, and in this case, they should be really easy to determine. So look at it, think about the ideal gas law, what the temperatures should be. Start with state 4, and think about, compare state 4 to state 1, and think about what should the temperature be in state 1 in comparison to state 4. So from 4 to 1, what kind of process is it? 4 to 1. Isochoric. So the volume hasn't changed. What happened to the pressure? It tripled. So what should the temperature do? It should triple. Yeah. You triple the pressure, keep the volume constant. It means you tripled the left side. So you must triple the right side. Triple 300, you got 900. So state 1, the pressure, the temperature should be 900. Okay. All right. So now think about state 2. What should the temperature? Tripled one more time, yeah. We kept the pressure constant, so that doesn't change anything, but we tripled the volume. So the left side of PV equal to nRT has tripled, so you need to triple the temperature yet one more time. So triple of 900 is? 2700, yeah. Let's go from 2 to 3. What happened? The pressure is a third. The volume is the same. So what must happen to the temperature? 1/3. So the temperature needs to be 1/3. So it would be back to 900. And then when you go from 3 to 1, the volume is 1/3. So 1/3 of 900 is 3. So that's that. So we didn't have to do much on that one, right? Now we need to fill out the next table and see if we can find any zeros. We would put those first. Those are the good numbers, easy ones. Any zeros?
2 to 3.
From 2 to 3, what's 0?
Work is 0.
Work is 0. So from 2 to 3, it's isochoric, so 0. And
4 to 1.
1 to 4 or 4 to 1, right? This one?
Yeah.
Yeah, okay. Good. And the other ones we actually have to do something. Okay? So we need to do this. It's diatomic, so we need to pay attention to that. CV is 5/2 R, and CP is 7/2 R. So I would do 1 to 2, and then 2 to 3, and then maybe 3 to 4 and 4 to 1. I'll just skip them. I will write the numbers. because they're basically the same. So from 1 to 2. From 1 to 2 it's isobaric. Isobaric, so the work done by the gas would be what? P times delta T, right? P times delta T. P is 3.039, and then delta V, the volume expanded, so it would be positive 1. So it went from 1 to 3. So 3 minus 1. Oh, I forget times 10 to the 5th. So here, times 10 to the 5th. So multiply that, you get 6.08 times 10 to the 5th. And then the cube, what do we do? NCV delta T. So we haven't found N. Well, maybe we need to do that. Okay. So N, we can use any of the states. N will be what? P1, let's say P1 over NR, over RT. R T1. And P1 is 3.039. The volume on state 1 is 1. And then like, oh, and then R. 8.314. We get the number of moles. 40.63. Okay. We can now do Q. So it's what? N C what? E. Delta T. So N is 40.63. CP. CP is 5.7 halves. Delta T. In going from 1 to 2, the temperature went from 900 to 27. I have 6.08, no, not 21.3 times 10 to the 5th. Okay. And you might be wondering, why didn't I put it 2.13 times 10 to the 6th? Good, but I see here 10 to the 5th. We're going to divide later, and so 10 to the 5th will go away, and that makes our life easier for calculations. Okay. We want to plug as less numbers as possible into the calculator, so we're less likely to make a mistake, and we're more efficient. Okay, for delta E thermal, you can do NCV delta T, right? You can do that. You can also do Q minus W. You can also do Q minus W. Q minus W is easy in this case, because you have the Q and you have the W. This one is to triple check your work, or double check your work. Right, so you can do this or that one. If you want to do this, I can give you money.